So in this video, I'm going to explain expectation, also known as mathematical expectation or expected value of a random variable. And that's really just the same thing as the mean of the probability distribution for that variable. So it's not really a new calculation, but we talk about expectation. It's often used in connection with things like gambling games or insurance or business ventures or situations like that where there's a chance of gaining or losing various different amounts of money. Sometimes you might win this much, sometimes you might win this much, sometimes you might not win anything, sometimes you might lose money, and the expectation, abbreviated E of X, for the expectation or expected value of that random variable, that represents kind of the average amount that you'd expect to win per game in the long run. And it could come out negative if in the long run you lose more than you win. So it's kind of a long run average of the amount you gain or lose per time you play the game, or per business venture, or per insurance policy. So let's start with a really dumb, simple example. So in this really dumb, simple gambling game, the way it works is we flip a coin. And if it comes up heads, I pay you $300. And if it comes up tails, you pay me $300. And I let you examine the coin. Make sure it's got a heads on one side, tails on the other side. It's completely fair. It's got a 50-50 chance of coming up either way. And so the amount that you win would be a random variable, and it could be positive 300 or it could be negative 300. So if we set this up as a probability distribution, the amount that you could win would be either positive 300 if it comes up tails, if it comes up heads, you win positive $300. If it comes up tails, you win negative $300. And the probability of each one of those would be 1/2 or 0.5. So if we calculated the mean of that distribution by taking each value times the probability of that value, 300 times 0.5 plus negative 300 times 0.5, and just so you know I'm not trying to pull something over on you, let me put this into the calculator. 300 times 0.5 plus negative 300 times 0.5 comes out to 0. So the expectation here, the expected value of this dumb little game is $0. And what that means is that if we played this any one time, you would either come out $300 ahead or $300 in the hole. But if we played this over and over and over again, you'd win about half the time and you'd lose about half the time. And those would tend to average out so that your long run average winnings would be $0 per game. And when this happens, when we get an expectation of 0, we call this a fair game. So a fair game in this sense is one where the expectation is exactly 0, and that means that neither side has any advantage over the other. In the long run, the wins and losses tend to balance out. Now, if you play the lottery or the slot machines or any casino game or anything like that, it's almost certainly not going to be a fair game in this sense of the word. That doesn't mean that they're trying to cheat you, that they're not being upfront about what the odds are, they've got things rigged. It just means that the probabilities of winning and the amounts you could win are set up so that in the long run, if out of all the people who play, all the times they play, lots and lots of times, the expectation is not going to be 0. That is, your long run average is not going to be breaking even. Instead, in the long run, the average, what happens to everybody who plays is that they're going to lose money. It has to be that way, otherwise the casino would not stay in business. They're in business to make money, and so even though an individual person might come out ahead, in the long run, out of everybody who plays, they're going to have to be spending more money than they win back, because otherwise the casino isn't going to make a profit and they're not going to be able to stay in business. Same thing with insurance. The insurance company has to take in more money than they pay out for people who have claims on their policy. Otherwise, they're not going to stay in business. So things like that are not a fair game in that sense of the word. Let's try another dumb example to get an idea of how this works. So the way this dumb gambling game works is you pay me $1 to pick a card out of a regular deck of cards. And if the card you pick turns out to be the King of Hearts, you win! Yay, you win $50. So the expected value of how much you'll win, let's see how we calculate that. First set up the amount that you win is either $50 if you're lucky and get the King of Hearts, or it's $0 if you get anything else. And the probabilities associated with those values. The probability of winning the $50 is 1 over 52. Because there's one way you could get the King of Hearts out of 52 cards you could pick. And then the other 51 out of 52 are not the King of Hearts, so you would win $0. Notice that each probability is somewhere between 0 and 1, and if I add them all together, they add up to 52 over 52, which is 1 exactly. So then if we calculate the expected value by taking each amount you could win times the probability of winning that amount, that would be $50 times 1 over 52 plus $0 times 51 over 52. That comes out to be about 0.98. Sorry, my bad, 0.96. Here's the calculation on the calculator. 50 times 1 over 52 plus 0 times 51 over 52 actually comes out to be 0.961538 something. But if you round it to 2 places after the decimal point, which makes sense because we're talking about money here, so to the nearest whole cent, that would be 96 cents. But remember, you had to pay me $1 to play this game in the first place. So the average winnings of 96 cents minus the $1 that you had to pay in the first place comes out to be a net loss of 4 cents. I keep forgetting to correct things. Sorry about that. Now what you see on the screen should be correct. You lose 4 cents on the average. That's not what happens on any particular game. On any particular game, you either come out $49 ahead or you come out $1 in the hole. But the average is a loss of 4 cents. It's an average gain of 96 cents minus the $1 that you had to pay each time. And another way we could figure this out is instead of having it set up so that our random variable is the amount that you win and then subtracting the $1 at the end, we could set it up so that the random variable is your net gain. Either you pay $1 and win $50, so you're $49 ahead, or you pay $1 and then you don't win anything, so you're $1 in the hole. That's a gain of -1. And if we just calculate the expectation based on that, 49 times 152 plus -1 times 51 over 52 does come out to be -0.04. So either way you look at it, you can figure the $1 fee into the random variable, or you can just subtract it at the end. Either way, you come out with an expectation with that included of negative 4 cents. Okay, another example. Going back to our example of the previous section where we had one $100 bill, three $20 bills, and 96 $1 bills in the bag, and you get to reach in and pick out one bill. The expected value of what you'll win, well, remember last time we set up our probability distribution, and it looked like this. The amount you win is either $100, $20, or $1. The probabilities associated with each of those dollar amounts we found last time were 1 cent or 0.01, 0.03, and 0.96. So to calculate the expected value, we take each dollar amount times the probability that goes with it and add those together. 100 times 0.01 plus 20 times 0.03 plus 1 times 0.96 comes out to be 2.56. So the expected value is 2.56. If you play this game over and over and over again, same bag of money each time, or you get a whole bunch of different people playing it over and over, the average amount that they win per game is $2.56. And if you had to pay $2.50 to play the game, then the expected value would be the $2.56 that you win back minus the $2.50 that you had to pay. So that comes out to be positive 0.06. That's in your favor. In the long run, you would tend to win back more than you pay by an average of 6 cents per game. So if you played over and over and over again, thousands of times, you'd expect to come out 6 cents ahead times the number of times you played. Now, what if you had to pay not $2.50 but $3 to play the game? Then the expected value would be, well, the $2.56 minus $3, so that would be negative 44 cents. Now you'd expect in the long run that you would come out in the hole. You'd be losing an average of 44 cents per game. How much would you have to pay to play in order for it to be a fair game? That is, in order for the expected value to be exactly 0. Well, you'd have to pay out exactly the same as the average amount that you win, namely $2.56. So if you had to pay exactly $2.56 to play this game that wins you back an average of $2.56, that would make it a fair game. The expected value then would be 0. Okay, one last example. A businesswoman evaluated a proposed venture. She estimated that it might be a good success and make her a profit of $9,000, and the probability of that happening would be 0.2. Or it might be still a success, but not quite as big a success. It might make her a profit of about $5,000. And the probability of that happening, she estimates to be 0.4. Or she might just break even with a probability of 0.3. Or she might lose money on the deal. She might lose about $4,000. And the probability of that happening is 0.1. So find the expected profit. So we need to take each possible amount she could gain times the probability of that amount. So we're calculating 9,000 times 0.2 plus 5,000 times 0.4 plus 0 times 0.3 plus negative 4,000 times 0.1. And that comes out to be $3,400. So first of all, that is positive. So this is worth investing in. It might lose her money, it might gain her money, but it's a pretty good bet. So in the long run, if she had a whole bunch of opportunities like this, they would average out to a profit of $3,400. And if she were comparing this against some other venture, she might want to compute the expected value of that and go with whichever one had the higher expected value.